Hey guys, this is Mr. Lowry. We're going to be working on this assignment, two-column proofs, segments and angles. We've been talking about two-column proofs, and last time we did an assignment that just was like algebra proofs to practice the structure of what a two-column proof looks like. Today we're going to take it one step further, and we're going to do two-column proofs with angle measurements and segment measurements and things like that. So the way this assignment is structured is that there's 4 pages, which seems like a lot, but I'm actually going to do half of these for you, and if you were in class, we covered a few of these in class as well. The idea here is that I'm going to do a proof for you here, show you what the structure looks like, and then you're just going to kind of use that same template, that same reasoning, to do a basically identical proof. The only difference is some of the numbers are a little bit different, and the figures a little bit different. Okay, so when you're learning how to do two-column proofs, it takes practice to figure out how to do that. And I understand that this can be a little bit tricky. So for each of these pages, I'm going to give you the first one. You are going to follow along on the second one on your own. Okay, and that's the same thing here. These proofs here on page 2 are actually really similar, basically identical. We just need to, I'm going to show you how to do it here. You're going to copy the template here. Okay, same thing with these angle proofs on page 3. And with these angle proofs on page 4. So I'm going to get you started here. In this video, I'm just going to do number 1 and then number 3, and then in a video coming up, I'm going to do 5 and 7 for you. Okay. Now, before we get started with this, you probably want to have this thing handy. If you don't have one of these, you can find one in Canvas and you can print it out. This is a copy of the notes we took. Now this was kind of a fill-in-the-blank notes again, and so I have the blanks filled in. But this page has properties of congruence for segments and for angles, and then it has the properties of equality that we talked about in our last lesson. So we're kind of doing a compare and contrast because some of these properties are kind of similar. Okay, also, as you read through, you'll notice that there's a different way to write a congruent statement versus an equality statement. The reason why that's important is an equality statement is basically an equation, okay? And when we have an equation, we can use all of these properties here of equality that we don't have for congruence. And so what you're going to see in some of our proofs is we're going to take a congruent statement that refers to shapes, and we're going to convert it into an equality statement which refers to measurements and essentially is an equation. And then we can use our properties of equality. On the back of this is some important postulates and definitions that we're going to use in this assignment we're about to do. So you should be familiar with the segment addition postulate and the angle addition postulate. If you're not, I would read through these, make sure you understand what that means, and then if you still need some help, there's a couple videos I posted to help you get started. And then there's some definitions down here, which some of these we already know, but again, we're going to refer to these on our assignment. Okay, so this basically all the properties that you're going to need for your assignment are on this worksheet, either on this page or on the page before it. Okay, so this is a really important handout for you. All right. When you are doing a two-column proof, this is basically an argument, a deductive argument. You're going to take steps on this side, make statements, and then you have to justify those statements that you make over here with a postulate or a definition or a property, basically some established mathematical fact. Okay, so that's what's going to go over here is a property, a definition, or a postulate. All right, let's get started. So when we're writing a proof, the first statement is always the given statement. So in this case, M is the midpoint of segment JK. All right, and the justification for that, the reason why we can say that, is that it was given to us. Okay, so that's the first statement. Sorry, let me just get organized here. The first statement is always just this guy, the given, and the justification is given. Now this is kind of like our thesis statement. We are setting out to prove. We're telling everybody this is what we're going to prove, and so this is going to be the last statement of our proof. Now we got to use logical deductive process to get to the next step. So we have to think to ourselves, what does midpoint mean to us? What does saying that M is the midpoint of this segment really tell us? Well, if you go back to the definition of midpoint, which is on our sheet here, It's a point that divides the segment into two smaller congruent segments. Okay, so what we can conclude from this midpoint idea is that this segment, JM, is congruent to this segment, MK. And so that's our next statement. So we're going to say segment JM is congruent to segment MK. Okay, sorry, this is an M over here. And the justification of that, the reason why we know that that's the case, is because of that definition of midpoint. All right, so what does that mean? Okay, again, we go a step further. So what does congruence mean? Or what do congruent segments mean? So again, we have a definition of congruent segments. It's segments that have equal measures. So if we have two congruent segments, then what we can do is we can use that definition to rewrite that congruent statement as basically an equation, right? So here we have shape is congruent to shape, and over here we have number is equal to number. So notice that this guy has a line over it, this AB doesn't. When it has the line over it, that means we're talking about the shape. When it has no line over it, that means we're talking about a number measurement. And if you need help with ideas with congruent segments and congruent angles, well, I think I posted a video there that you can check out on like the segment addition postulate and the angle addition postulate. I might go back and look at those. Okay. All right, sorry, moving on. So what we have here is that if this segment is congruent to this segment, what we conclude from there is that the measurement, or the distance from J to M, is equal to the distance from M to K. Now that may not seem like a very different step, but this is actually a really important step to make, going from step 2 to step 3. The reason why is this right here is a congruent statement, and this right here is an equality statement or an equation. And if you think about our properties, we have way more properties that work with equations than we do that work with congruence. So with equations, we can do multiplication and division, we can do addition and subtraction, we can do substitution, we can distribute, but we can't do those things over here. So this translation here from congruence to equality is actually really important. And the way we justify that is we just say that's the definition of congruent segments. That's what it means for two things to be congruent. Okay, step 4. So what does it mean if JM, that measurement, is equal to MK, that measurement? Well, notice that we have these expressions here that represent those measurements. So what I can do is I can replace JM with 7x plus 5, and I can replace MK with 8x. Basically, I'm substituting here, right? So I'm going to do the substitution property of equality. All right, now this is actually kind of familiar. Now that we have this, we have basically an equation here, an algebraic equation. We know how to solve this. We practiced this already. So what we would do is we would subtract 7x from both sides. Now we don't show that happening, like I don't write minus 7x. I just give you the next step. So if I subtracted 7x from the left, it'd be gone. I'd be left with a 5. If I subtract 7x from the right, I would end up with just a 1x. Okay, and that is the subtraction property of equality. Okay, so what we really want to do is we want to show that JK, that whole thing, is equal to 80, right? Well, we have x, and so if we plug in x, we're going to be able to like add these together and get the rest of the whole measurement. Okay, now there's a couple steps that we need to do in order to get there, because we want to go step by step here. The first thing I would do is I would just say that JM and MK together is going to equal JK. So the measurement from J to M, if I add that to the measurement from M to K, I'm going to get the whole measurement from J all the way to K. And that is the segment addition postulate. If you add up the small measurement to the small measurement, you get the measurement of the entire long segment. So if you're not familiar with the segment addition postulate yet, I would go check out the videos that I posted or read what I wrote on your note sheet. so you can get familiar with how that works. So notice that all of my justifications are either definitions or properties or postulates, right? They're mathematical facts that we already have established in some way. Okay, so now what I'm going to do is I'm going to do some substitution. Okay, we already kind of did a similar step like this before, but I know that Jm I can write as 7x plus 5, and I know mk I can write as 8x, and that's going to equal jk. Right? Now that's a substitution because I'm substituting this expression for this. And I'm going to keep substituting. So I'm going to wait on the justification for just a second because a lot of these are going to be substitution, and I'm just going to write substitution one time. Okay, now I'm going to replace 7x and 8x with a 15x because 7x plus 8x is 15x. So I'm replacing two things with what they're equal to. Again, that's called substitution. Now there's also kind of a hidden property happening here that, if we wanted to, we could rearrange these so they're next to each other, right? Like I could move the 5 over here and the 8x over here. That would be the commutative property of addition. But basically what we're kind of doing here is we're combining like terms. And since there's not a combined like terms property, what we write for the reason is just substitution. Okay, a couple more substitutions here. We're going to replace x with 5 because remember up here 5 was equal to x. Okay. And now what we're going to do is we're basically going to, we're on 10. We're going to evaluate this, right? So 15 times 5 is 75. I add that to 5 and I get 80. So 80 equals jk. Again, all of that was substitution. We're just replacing pieces like one piece at a time. So I'm going to write substitution property of equality. And then I'm just going to kind of draw an arrow because these are all the same justification. This is just a substitution and another substitution and another substitution. All right, now it looks like we need one extra line. That's okay. I don't always know exactly how many lines these are going to take, so you may use less lines or more lines depending on the proof you're doing. This looks like we're going to have one more line because we almost proved what we wanted to. jk equals 80. Well, we have 80 equals jk, and we know that that is equivalent, but since this is an argument that we're trying to make and we're trying to justify each step, we're going to take one more step to reverse the order of those things, and that property is the symmetric property of equality. All right, so that is kind of how you manage this proof. Notice that there's an important shift here from congruent statement to equality statement, and then pretty much it's kind of algebra for a while, and you plug it back in. The algebra stuff we've practiced, the properties of congruence and the definitions and the postulates and stuff are a little bit new, and so now we're kind of combining these two ideas. Now what you're going to do is you're going to go down here and you're going to basically do the same thing. You're going to try to copy that same idea in number 2. Okay, use the same kind of process. You can use the same order. The only difference is instead of using JKs and MKs, you're going to use BAs and ACs and things like that. So you may not be ready to do a proof like this on your own because it's kind of tricky, and we're just barely figuring out how to do these. But you should be able to follow along here and then kind of copy that chain of reasoning. Okay, we're going to do one more in this video, and then we'll stop, and I'll do the next two in the next video. Okay, so here's another one. Now, there's no numbers here, but it'll still work out. We're just going to kind of use variables basically to represent everything. And before we start, there's an important idea that I want to talk about really quick, and it has to do with the addition property of equality. A while ago, we solved what we call systems of equations. Let me show you what that looks like. Okay, this is a system of linear equations, and what we talked about is if we have two equations, what we can do is add them together to get a third true equation. So in this context, what we would do is we do 3x plus 2x, and that gives us a 5x. And then a negative 2y and a positive 2y cancel, which is called elimination, and then we get equals 25. Okay, The point that I want to show you is what we're doing here when we do this. This is called the addition property of equality, or it's one application of the addition property of equality. So I can add two equations together to get a third equation that is also true. And we're going to actually do that in this proof. Okay, so setting up the proof. The first thing we're going to need to do is we're going to need to repeat the given statement, because that's where we're going to start. So segment AY is congruent to segment XY. Segment YB is congruent to segment YZ. Okay. Now sometimes what I like to do when I'm doing a proof is label the figure to help me out. So if AY is congruent to XY, I can put like a little tick mark here and here to show that these two guys are congruent to each other. Okay. And then YB is congruent to YZ. So again, little tick mark. So these two guys are congruent to each other, and these two guys are congruent to each other. Now I don't have to really justify that with a definition or property or postulate, because that's the starting statement. Now this is kind of like my thesis. I'm setting out to prove that AB, this whole thing, is equal to XZ, this whole thing. That's like my claim. We can't just say it, we got to support it. We're going to make an argument here. We got to support this claim with specific details. So let's talk about what we know from congruence. What does congruence really tell us? If I told you that AY was congruent to XY, what does that mean to you? Well, it means the measurement of this segment is equal to the measurement of this segment. And so again, we change this congruence statement into basically an equation, right? We get rid of the lines on top. We get rid of the little swooshy on the equal sign. Because now we're not talking about shapes anymore. We're talking about numbers. Okay, we don't know what measurement is, but let's say, for example, this is 10 and this is 10. We don't know that's for sure, but now we're saying 10 equals 10 instead of this segment is the same length as this segment. So we have an equation. Okay, likewise, we can kind of think of it like these two are the same measurement as well. Now again, we don't know that it's actually 10 and actually 5. That's just a kind of an example. But what I could say is that YB, which just represents a number, is equal to YZ, which just represents some other number. So now we have equations. And equations are great because we have lots of properties that we can use with equations, like the addition property of equality, okay? Which is where we're going next. So I showed you this over here, this addition property of equality business. You can actually do that with these kinds of equations as well. So these are two linear equations. Notice these are just equations like any other equation. This represents a number, and so does this, and this represents a number, and so does this. So off to the side here, I'm going to show you what's happening here. This is kind of weird, but I'm going to take this equation, AY equals XY, and I'm going to add it to this equation, YB equals YZ. And what we're going to get is AY plus YB equals XY plus YZ. Since I don't know what numbers they are, I can't really like combine them, but I'll just put them next to each other. Okay, so our next statement is AY plus YB is equal to XY plus YZ. Okay, so think about what we're doing is really quick. What we're basically saying is that if I take this segment and I add it to this segment, that's going to be equal to this segment adding to this segment. Right? And I can do that because I already know these two guys are equal and these two guys are equal. So I'm basically adding equals to equals and saying that the results are equal. Okay? That's the addition property of equality. Okay, just noticing that I missed a justification here, or a reason. So going from here to here, again, when I translate from a congruent statement to an equation or an equality statement, I do that because I know that the definition of congruent segments is that their measures are equal. So the justification here is definition of congruent segments. I think I said angles, sorry, I meant segments. Okay, cool. All right. So what I just said in the last statement, statement 3, is that if I take this segment and I add it to this segment, that's going to be equal to the sum of this segment and this segment in terms of measurements. So this measurement plus this measurement is equal to this measurement plus this measurement. That's kind of like saying 10 plus 5 is equal to 10 plus 5, right? Now what we know, though, is we know what 10 plus 5 is. It's 15. Well, we can't use real numbers here because we didn't start with real numbers. What we have to say is 10 plus 5 is equal to 15, but in like notation, in segment notation. So what I'm going to say is AY plus YB, AY plus YB is equal to the whole segment from A to B. So from A to Y and from Y to B is equal to the whole segment from A to B. Okay, now the way that I can say that, when I say that two smaller segments add to the bigger segment, that's the segment addition postulate. Okay, you can actually kind of say two things in the same line, or we can do two separate lines. It doesn't really matter. I kind of ran out of room. But what I'm going to do is I'm going to say a very similar statement about this line. So xy plus yz is equal to xz, right? The small plus the small measurement plus the small measurement is equal to the long measurement. So going back up to the top, or up to 5 here, xy plus yz is equal to xz. Okay, both of those are the segment addition postulate. So I'm just going to draw an arrow. Another thing that you'll see sometimes is people will just do quotation marks like this, which means same as above. Okay, so you can do that if you want to. Okay, so let's talk about where we're at. We know that AY plus YB is equal to XY plus YZ. Okay, but we know that this is equal to AB, and we know that this is equal to XZ. And so what we do here is we're gonna basically rewrite step 3, but we're gonna replace AY plus YB with AB, and we're gonna replace XY plus YZ with XZ. And that's a substitution. We're replacing this with what it's equal to, and we're replacing this with what it's equal to. So that is the substitution property of equality. Okay, now we're basically where we wanted to be, right? We were out to prove that segment AB is congruent to segment XZ, and we're almost there. But remember, this is not an equality statement. This is an equation. This is like saying 15 is equal to 15. And what we really want to say is a segment is congruent to a segment, because these just represent some number. In our example here, that would be like 15 equals 15. All right, so let's change this now, convert it back to a congruent statement. Segment AB is congruent to segment XZ. And we can do that because the definition of congruent segments is that their measures are equal. So if we know their measures are equal, we can say they're congruent by the definition of congruent segments. Okay, and that's our proof. So this is a practice in deductive reasoning, deductive logic. All right, we're using properties to get from one point to another point, to get from a given statement to a conclusion. And we can't just say it's true. We have to like show that it's true. We have to make statements that showing it's true with supporting details. All right, now this guy right here is very, very similar. Sorry, I'm just double checking to make sure that this is right before I see. JK is congruent to NM, and KL is congruent to ML. Okay, cool. That's going to look good. All right, so the process of solving this guy, or excuse me, not solving, but proving this thing is very, very, very similar to this. It's going to be like the same exact steps. The only difference is you're not going to have A's and Y's and X's and B's. You're going to have J's and K's and L's and M's. But we can kind of start labeling this. JK is congruent to NM, and KL is congruent to ML. Right? So it's like the same thing, only these don't cross, but it doesn't really matter. It doesn't matter that they cross. In fact, it'll probably make it easier because you don't have to, have too many Y's in there. So follow this structure here to do this proof. Okay, I don't expect you to know how to do it on your own. Just follow the example here down here so you can practice using these properties. Okay, we got 2 more that I'm going to do examples for, and I will do those in another video. Thanks for watching.